Hello and welcome back to Introductory Astronomy. Our study of stellar evolution has led us to some very unusual and unexpected objects. We talked about red giants, white dwarfs, and supernovae, and these are extreme states of matter completely unfamiliar to us here on Earth. Yet stellar evolution, and in particular its endpoint, the death of a star, can have even more bizarre consequences. The strangest states of all result from the catastrophic implosion-explosion of stars much more massive than our Sun. The almost unimaginable violence of a supernova may bring into being objects so extreme in their behavior that they require us to reconsider some of our most sacred laws of physics. They definitely open up a science fiction writer's dream of fantastic phenomena. They may even one day force scientists to construct a whole new theory of the universe. This picture you see right here is a stunning composite image of 3 different images taken by telescopes in orbit. The optical light part, shown here in yellow, was observed by the Hubble Space Telescope. X-ray radiation, shown in blue and green, with the Chandra Telescope, and infrared radiation, shown in red, with the Spitzer Telescope. This object is known as Cassiopeia A, the remnant of a supernova whose radiation first reached Earth about 300 years ago. The small turquoise dot at the center, if you look very closely, may be a neutron star created in the blast, the sole survivor of the explosion. So in this chapter, we're going to talk a little bit about neutron stars, pulsars, neutron star binaries, gamma ray bursts, my favorite black holes, a very general overview of Einstein's theories of relativity, the idea of space travel near the black holes, and the observational evidence that we do now have of black holes. Because originally black holes were theorized, and a few years later we were able to observe them. Now, after a type 1 supernova, little or nothing remains of the original star. After a type 2 supernova, part of the core may survive. It is very dense as an atomic nucleus, and it is called a neutron star. And as the name implies, neutron stars are composed almost entirely of tightly packed neutrons. Neutron stars may have 1 to 3 solar masses, but they're so very dense that they end up being very small. This image here shows a 1 solar mass neutron star that is only 10 kilometers in diameter, about the size of Manhattan Island. So imagine our whole sun being compressed to such a density that all its mass is fit into 10 kilometers in diameter. That's indeed a very, very dense object. Some other important properties of neutron stars, one of them is rotation. As the parent star collapses, the neutron core spins very rapidly in order to conserve angular momentum. So it ends up having typical periods of a few fractions of a second. So it's spinning very, very fast. Magnetic fields, a neutron star ends up having an enormously strong magnetic field, and this is a result of its collapse. Pulsars. The first pulsar was discovered in 1967. It emitted extraordinarily regular pulses, and nothing like that had ever been seen before. After some initial confusion, it was realized that this was a neutron star spinning very, very rapidly. So, pulsar radiation emit periodic bursts of radiation. This recording in the picture right here, which is intensity versus time in second, shows the regular change in the intensity of the radio radiation emitted by the first pulsar discovered, known as CP1919. Some of the object's pulses are marked by arrows. But why would a neutron star flash on and off? This figure illustrates the lighthouse effect responsible. So we have strong jets of matter emitted at the magnetic poles. If the rotation axis is not the same as the magnetic axis, the two beams will sweep out circular paths. If the Earth happens to lie in one of those paths, then we will see the star pulse. So let's take a look at this diagram a little bit more closely. Charged particles, accelerated by the magnetism of the neutron star, will flow along the magnetic field lines, and this is going to result in radiation that beams outward. At greater distances from the star, the field lines channel these particles into a high-speed outflow in the star's equatorial plane, forming a pulsar wind. The beam sweeps across the sky as the neutron star rotates. If it happens to intersect the Earth, then we see a pulsar, much like a lighthouse beacon. Pulsars radiate their energy away very rapidly. The radiation weakens and stops in a few tens of millions of years, making the neutron star virtually undetectable. Again, pulsars will not be visible on Earth if their jets are not pointing in our line of sight. There is a pulsar at the center of the Crab Nebula. The images here show it in the off and on state. The disk and jets are also visible in frame B. It is only 950 years old, and it is still so powerful it emits photons all across the electromagnetic spectrum. So let's take a look at each picture more carefully. In frame A, we see the Crab pulsar in the core of the Crab Nebula. In frame C, we have the blinking on and off of the pulsar, and it happens about 30 times each second. This is a pair of optical images, and you can see in the off state, you don't see anything where the arrow is located at, compared to the on state where you see the arrow and you see a big blob. In frame B, we have a more recent Chandra X-ray image of the crab superimposed on a Hubble optical image, and it shows the central pulsar as well as rings of hot X-ray emitting gas in the equatorial plane, driven by the pulsar wind and moving rapidly outward. Also visible in the image is a jet of hot gas, not the beam of radiation from the pulsar, and it's escaping perpendicular to the equatorial plane. Finally, in frame D, we have a light curve, and it shows the main pulse and its precursor. The latter is probably related to the beam directed away from the Earth. The Crab pulsar also pulses in the gamma-ray spectrum. In frame B, you see a sequence of Compton gamma-ray observatory images showing Geminga's 0.24-second pulse period. The Crab's 33 millisecond period is too rapid to be resolved by the detector. If you take a look at frame A, we see the Crab and Geminga pulsars, which happen to lie fairly close, about 4.5 degrees to one another in the sky. Unlike the Crab, Geminga is barely visible at optical wavelengths and undetectable in the radio region of the spectrum. Some other important properties of neutron stars. We have the pulsar wind. Roughly 99.9% of the energy flowing away from a pulsar is carried as a pulsar wind of high-speed atomic particles. This can produce small, high-energy nebulae in the vicinity of the pulsar. Supernova remnants. Many supernova remnants probably do contain pulsars, but their beams never sweep over the Earth. Also, some pulsars move through space at high velocity, quickly leaving their supernova remnants behind. Neutron star binaries. Bursts of X-rays have been observed near the center of our galaxy. A typical one appears below, as imaged in the X-ray spectrum. An X-ray burster in general produces a sudden, intense flash of X-rays, followed by a period of relative inactivity lasting as long as several hours. Then another burst occurs. These bursts are thought to be caused by explosive nuclear burning on the surface of an accreting neutron star, similar to the explosions on a white dwarf that give rise to novae. In frame A, we have an optical photograph of the globular star cluster Tarzan 2, showing a 2 arcsecond radius dot at the center where the X-ray bursts originate. Frame B is the X-ray images taken before and during the outburst. The most intense X-rays correspond to the position of the black dot shown in A along that arrow. These X-ray bursts are thought to originate on neutron stars that have binary partners. Again, this process is similar to a nova, but much more energy is emitted due to the extremely strong gravitational field of the neutron star. If we take a look at frame A, we see how matter flows from a normal star toward a compact neutron star companion and falls toward the surface in an accretion disk. As the gas spirals inward under the neutron star's intense gravity, it heats up, becoming so hot that it emits X-rays. In at least one instance, the peculiar object SS-433, some material may be ejected in the form of 2 high-speed jets of gas. Frame B is false color radiographs of SS-433 made at monthly intervals from left to right. You can see the jets moving outward and the central source rotating under the gravitational influence of the companion star. Most pulsars have periods between 0.03 and 0.3 seconds, but a new class of pulsar was discovered in the early 1980s, and that's the millisecond pulsar. In this image here, you see a millisecond pulsar gas from a companion star spiraling down onto the surface of a neutron star. As the infalling matter strikes the star, it moves almost parallel to the surface, so it tends to make the star spin faster. Eventually, this process can result in a millisecond pulsar, a neutron star spinning at the incredible rate of hundreds of revolutions per second. Millisecond pulsars are thought to be spun up by matter falling in from a companion. This globular cluster has been found to have 108 separate X-ray sources, about half of which are thought to be millisecond pulsars. This dense core of cluster 47 Tucani, shown in frame A, harbors more than 100 separate X-ray sources. More than half of these are thought to be millisecond pulsars, so they're not as usual as we thought, and they're still accreting small amounts of gas from their companions after an earlier period of mass transfer spun them up to millisecond speeds. So we're talking about unimaginable speeds. They're rotating extremely fast. In 1992, a pulsar was discovered whose period had unexpected but very regular variations. These variations were thought to be consistent with a planet, which must have been picked up by the neutron star, not the progenitor star. So let's take a look at the images. A neutron star can encounter a binary made up of two low-mass stars, ejecting one of them and taking its place. This mechanism provides a means of forming a binary system with a neutron star component, which later may evolve into a millisecond pulsar, without having to explain how the binary survived the supernova explosion that formed the neutron star. So that's one possible scenario. Which brings us to gamma-ray bursts. They were first spotted by satellites looking for violations of nuclear test ban treaties. This map of where the bursts have been observed shows no clumping of bursts anywhere, particularly not within the Milky Way. Therefore, the bursts must originate from outside our galaxy. In frame B, we see positions on the sky of all the gamma-ray bursts detected by Compton Observatory during its nearly 9-year operating lifetime. The bursts appear to be distributed isotropically, meaning uniformly, across the entire sky. The plane of the Milky Way galaxy runs horizontally across the center of this map, which is also the direction to the center of our galaxy. Frame A shows plots of intensity versus time in seconds for 3 gamma-ray bursts. Note the substantial differences between them. Some bursts are irregular and spiky, when others are much more smoothly varying. Whether this wide variation in the burst appearance means that more than one physical process is at work is presently unknown. And this data was taken by NASA. Now, distance measurements of some gamma-ray bursts show them to be very far away. We're talking about distances of billions of parsecs. Occasionally, the spectrum of a burst can be measured, allowing distance determination. Here we see the gamma-ray burst counterparts. We have optical images of the gamma-ray burst, GRB, 971214. The numbers simply mean December 14, 1997, the day the burst was recorded. In image A, which was taken with the Keck telescope, we see the visible afterglow of the gamma-ray source, look at the arrow, and it is quite bright, comparable to 2 other prominent sources in the overlaid box. A spectrum of the afterglow showed it to be highly redshifted, placing it near the limits of the observable universe, almost 5 billion parsecs away. By the time the Hubble image B was taken, about 2 months after the Keck image and 4 months after the initial burst of gamma rays was detected by the Italian-Dutch Bepo-SAC satellite, the afterglow had faded, but a faint image of a host galaxy remains. The different colors result from the use of different filters to observe the light. A model for gamma-ray bursts. At least some gamma-ray bursts are probably related to the deaths of very massive stars, greater than 25 solar masses. In a supernova-like explosion of stars that are this massive, the core might collapse not into a neutron star, but directly onto a black hole. Such stellar explosions are termed hypernovae. If you take a look at this sequence of pictures starting from the top, we have the collapsing core of a massive star that drives its energy along the axis of rotation. Because the rotation of the star slows the collapse of the equatorial regions, and within seconds the remaining parts of the star fall in, beams of gas and radiation strike surrounding gas and generate beams of gamma rays. The gamma ray burst fades in seconds, and a hot accretion disk is left around a black hole. Two models have been proposed to explain gamma ray bursts. In frame A, we see the merger of two neutron stars. In frame B, we see the core collapse, implosion, and stalled supernova or hypernova of a single massive star. Both models predict a relativistic fireball, perhaps releasing energy in the form of jets as shown. Study chapter 22.1 through 22.4 and be able to explain what are neutron stars and pulsars and how they each formed. Be able to discuss the basic characteristics of gamma ray bursts and the current theories attempting to explain them. Until next time.